Okay. Seems we are live. Okay, so then let's start. Yeah, welcome everyone. It's my great pleasure to introduce Karina and Stefan, who are PhD candidates at the Cluster of Excellence in Bochum, and are associated to the Max Planck Institute for Security and Privacy. Karina is focusing in her research on human problem solving in hardware reverse engineering. And in particular, she is strongly interested in exploring how engineers analyze an unknown chip design and how to derive first ideas from the development of novel forms of countermeasures in terms of hardware reverse engineering. And Stefan is also working on hardware security. In his research, he aims to render hardware more secure against reverse engineering attacks by studying the human factors involved in reverse engineering. And beyond that, he is also very interested in the end user perception and behavior regarding security and privacy. So yeah, and it's my great pleasure to have both of them here today and present us their latest research towards cognitive obfuscation, where they are trying to understand the cognitive processes of hardware reverse engineers. Karina and Stefan, the floor is yours.
Philip, thank you so much for your kind introduction, and thank you for having us here in the security seminar. So yeah, my name is Stefan, obviously, and I'm presenting today with Karina. And as you already said, we are both last year PhD students at the Ruhr University of Bochum. And today we would like to tell you a little bit about our research and also about our PhD journey of the last 4 years. So if you would go to the next slide. So just a little bit of background where we are from. We would love to be in London today. We would have loved to visit you and, take the ferry and everything. But this is where we actually are. We are in Bochum. It used to be a coal mining town. So at some point we had over 250 active coal mines. But nowadays we like to sell ourselves as an education town. And especially in the area of security, we have over 200 researchers here now, professors, PhD students, postdocs, who are on this lovely campus university, one of the few campus universities in Germany, actually. And yeah, we do a lot of interesting research, and about one of those topics we will tell you today.
Okay. Yeah. Hello, everyone. It's a pleasure to be here, and yeah, I will give a short overview about our project. This project started about 4 years ago at the graduate school called SecHUMAN at the Ruhr University at Bochum. And the aim of this project was to investigate or to explore the technical and cognitive processes that may or might play a role in hardware reverse engineering. And yeah, for this purpose, an interdisciplinary approach was essential, and therefore the team consists of the hardware security squad, represented by Stefan and his supervisor Christoph Paar, and on the other hand, the psychology squad with my supervisor Nicole and yeah, myself. And yeah, over the past few years, we have been able to develop our results in collaboration with international companies such as Google or Intel or Infineon, or with other universities like the University of Massachusetts in Amherst, USA. Yeah, and we've also had the opportunity to present our approaches and initial findings twice at Security and Human Behaviors at Harvard University and Carnegie Mellon. And yeah, today we will give an overview about our past 4 years as PhD students. And yeah, following, Stefan will give you a short overview and define and explain what hardware reverse engineering is. Yeah. Okay.
Right. So I will start with some technical stuff, but I'm not gonna make it too technical. But I'm gonna give an overview about the technical backgrounds actually of hardware reverse engineering. So if we want to reverse engineer something, we always have to see also the engineering process. And if we engineer hardware, then we start with a blank sheet of paper. And we define what our hardware should do, and then there are several steps of digital design, but also of physical fabrication, which usually happen in a very distributed fashion. Before I have a microchip, and this microchip will then be assembled on a PCB, on a printed circuit board. If you do the next animation, Karina. Mm-hmm. And those printed circuit boards we have in all our daily used electronic devices, such as smartphones, but also in the critical infrastructure, like the telecommunication infrastructure, or like airplanes. And now we can also go the way back. We can disassemble a smartphone. We can take out the PCB. This is known as product tear down. People do that when a new iPhone comes out, and they identify the components, and then they say what each component would cost. Yeah, and maybe they would detect like a component which doesn't belong there or something. Yeah, we've had this before. But then from the PCB, from the printed circuit board, you take the microchip again, and then you can also inspect this microchip. Yeah, this is what we mean by hardware reverse engineering. So the steps of inspecting the microchips, and this has like a multitude of different applications. There are legitimate applications. For example, if a company wants to find out if another company infringed on their intellectual property. But then there are also illegitimate applications. For example, the extraction of cryptographic secrets, but you would also need it if you want to actually to infringe IP. Now we're going to take a look into the steps of hardware reverse engineering. So you can start with an ASIC, with an application-specific integrated circuit. It comes in a package, which you usually need to remove by some mechanical or even chemical means. And then the structure of such a microchip, they are three-dimensional. So on the lowest layers, usually on the two lowest layers, you have Boolean logic, you have Boolean gates and flip-flops. And then all the other layers, and there can be up to 20 other layers, are the routing. So they connect the Boolean gates. So you have to delayer this, also usually with chemical methods. And then you take a scanning electron microscope, or a focused ion beam to make images of those very small structures. And once you have those images, then kind of the physical processes end, and you continue on your computer. So you stitch those images back together, and you extract a so-called netlist from that. And when you have extracted this netlist, this is actually when kind of our work, or what we investigate, begins. So then you have to actually make sense of this netlist and to find out what this netlist does. There's another way where we come from. We can come from the so-called field programmable gate arrays, which is another type of hardware. We can also extract netlists from those. Those FPGAs are configured with so-called bit streams. They have configurable logic elements. And then if you know like the mapping of this bit stream, if you reverse engineer the mapping of this bit stream to the logical elements, you can also extract a netlist. There are also other ways to obtain a netlist. For example, if you like just steal it from somewhere, basically. But those are the physical ways to get a netlist. And then, as I just mentioned, the core of our research is this netlist analysis. And here we see how one might imagine this looks like. Yeah, so I have my smartphone, I disassemble it, I inspect the microchip, and then it usually, it has several functions, and you could imagine, oh, it looks like this. It's very neat. There's a CPU, there's an advanced encryption standard core, there's a hash function, and there's the communication core for the periphery. But actually, it looks very different. This is the so-called sea of gates what you can see here in this animation. And the design steps would have optimized all hierarchization, all module boundaries, and also in comparison to let's say software reverse engineering, when you extract a netlist from a microchip, you never have any meaningful descriptions or variable names available, which could help you in your reverse engineering process. So based on the technical research literature and also on real-world insights from experts working on this topic, we came up with this model of netlist reverse engineering. So on the one hand, there are a lot of semi-automated processing steps, like to detect components. It's usually via template matching that you already know, like maybe how an adder might look like in a netlist, and then you can find out if there are adders in your netlist. So you have a lot of those small algorithms which will help you to abstract this sea of gates. But then those processes are always steered by a human analyst and by the cognitive processes of a human analyst. And those cognitive processes actually remain very poorly understood at the beginning of our research. And so the goal of our research was to develop and quantify novel countermeasures against reverse engineering. For example, this could help for IP protection, to make reverse engineering harder. But to do that, we first have to understand the cognitive processes which influence the success of reverse engineering. And Karina will tell you a little bit more about the psychological background now.
As you may imagine, there was not much research in this area. We had to do a lot of research to identify if there were any researchers who were working in the same field like we plan to do. And during the project, we became aware of an article that by not dealing with cognitive processes in hardware reverse engineering, they looked at the cognitive processes in a very related field. And this article from then embedded or enabled us to embed our research not only in the technical community, but also in the cognitive psychology community. And this article I'm referring to was published by Lee and Johnson Lair. Some of you might know Johnson Lair. He's a quite famous psychologist who defined and developed the concept of mental models. And they conducted in 2013 5 laboratory experiments and defined that the approach of reverse engineering of Boolean functions may be a specific form of human problem solving, which is strongly understudied by now. And during the task in these experiments, the participants were asked to draw simplified electrical circuits that would match to a shown lamp or water flowing systems. So it's definitely hard to compare to the realistic hardware reverse engineering task Steffen previously mentioned. But Boolean functions also play a major role in the hardware reverse engineering field. And based on this preliminary work by Lee and Johnson Lair, we then also assumed from this point on that hardware reverse engineering is about human problem-solving processes, which had to be investigated in greater detail. And in general, problem solving is characterized as an essential cognitive ability and a key competence necessary to handle complex situations in our daily lives, and also in solving hardware reverse engineering tasks. And when confronted with the problem solver usually lacks in the knowledge for producing an immediate and routine solution. And in order to achieve a desired goal state, so this means the problem solution, the problem solver applies a series of cognitive operators, which may be specific actions or generic problem solving strategies. And in the following, I will just give a short introduction about how we imagine the HRE problem solving process in our scenario. So in the beginning of a problem solving setting, the problem solver, in this case, our hardware reverse engineer, is in the so-called initial state, in which he or she or they lack an immediate solution to solve the current task. And they can reach the solution or the so-called goal state by applying a set of generic or specific problem solving strategies. And in terms of hardware reverse engineering, the initial state in our case is that the problem solver has the netlist of the chip. And by making sense of semi-automated netlist analysis steps, the engineer may try to reach the goal state of receiving a high-level description of the chip design, or to identify specific components of interest, such as an infinite state machine, which is implemented in the netlist. And the process of the hardware reverse engineering problem solving may be described as a multi-step process. So the reverse engineer selects in the beginning a range of actions and operators, so-called strategies, to transform the initial state into the goal state in order to identify the crucial components or to fulfill the task. And therefore, the engineer may apply prior domain-specific knowledge, such as knowledge about chip architectures or Boolean functions, in order to change the states and to make the decisions or to manipulate information in order to select novel strategies. And during this problem-solving process, it has been shown by prior research in other domains that the problem solver also needs to acquire and to identify novel information. And the problem solver also learns and acquires new domain-specific knowledge. This in turn also influences the actions that are selected again to keep the transformation going. Previously, when our project started in 2016, I mentioned this. There were not much work in this field, and with former colleagues and PhD students who have already finished their PhDs, we wrote a paper and published this in 2017 and gave a short overview about what is hardware reverse engineering and what needs to be done in this specific field of cybersecurity. And as far as we know, we were the first researchers who aimed to investigate and explore cognitive processes of hardware reverse engineers in order to develop countermeasures. And this was the first paper we wrote. And the start of the project was anything but easy, because we were faced with the following methodological problem. Does anyone know any hardware reverse engineers? And because researchers who aim to conduct experimental studies in hardware reverse engineering must contend with the methodological problem that hardware reverse engineer experts are usually unavailable for research. Because the worldwide population of experts is very small, we first had difficulties to locate them, which was not only very time consuming, but also often very unsuccessful. This already small population was further narrowed when we consider that hardware reverse engineering experts often work for highly specialized companies or even for government agencies that impose contractual restrictions that forbid them from disclosing any details of their work, including their working processes. So this was a tough start in the project, because we thought we can recruit 20 experts and let them solve a realistic hardware reverse engineering task, but this was not the way we had to go. So otherwise potentially willing candidates are consequently unable to participate in our research. So what to do? This was the first question we asked ourselves, and we developed a methodological approach consisting of 3 main points. And of course, our approach also included that if somehow possible, we would also like to investigate how hardware reverse engineering experts solve realistic HRE tasks. So this was also and always a part of our approach. But in addition to studying and observing HRE experts, however, we also saw the opportunity for insights by studying non-experts. And by non-experts, we do not mean complete beginners, but reverse engineers on intermediate levels of expertise in this field. So this was the second part, the second phase, if you want to, of our methodological approach to get started, but to explore cognitive processes and factors in hardware reverse engineering. And beside those 2 approaches,
Can I ask a quick question?
Yeah, sure.
So how did you distinguish the HRE experts from the non-experts? Was this like an amount of like experience in terms of like years that they have worked or degrees that they collected, or?
Yeah, you're quite right. Yeah, we asked them to celebrate their experience, which included years of experience in working in specific fields, in solving specific tasks, in their weekly amount of working on Netlist and on analyzing Netlist. So we had a questionnaire too. Yeah.
Okay. But actually, we hardly got any expert reverse engineers to fill out our questionnaire. So you will see in the following, there's one who actually did the tasks. Others we could talk to, but they didn't want to do any questionnaires or stuff with us.
We traveled to Portland and talked to Intel engineers, and we also asked Google, but
I can imagine that this is hard.
Okay. And besides those two approaches, we also developed the idea to observe hardware reverse engineering problem solving in a so-called knowledge-free environment. That may allow us to recruit larger samples of people who do not necessarily have the amount of knowledge in order to solve a specific hardware reverse engineering task. We will come to this third point later because it's part of our next steps on our future research, and we will focus in the next slides on observing problem solving by one HRE expert and by observing problem solving of hardware reverse engineering intermediates. Okay. So at the beginning of the project, we were not able to recruit any HRE experts as participants for our study, but we wanted to start, right? We wanted to get started and to conduct some studies which may shed some light on the unexplored cognitive processes in hardware reverse engineering. And in order to start the project, we decided to train a sample of people who are not hardware reverse engineering expert, but who have a certain level of knowledge and skills in the cybersecurity area, but also maybe in the hardware reverse engineering area. And for this purpose, we used the infrastructure of two universities. On the one hand, we used the infrastructure of the Ruhr Universität, but also of the one American university, the UMass in Amherst. And both universities train cybersecurity students who also deal with hardware, among other things. So it was clear that we had to try to provide these students with relevant prior knowledge and skills in HRE in order to prepare them to participate in our study and to get started with this project. And from this, the idea grew that to develop a hardware reverse engineering course that could be taught at both universities. And this course should fulfill two main points. First, we aim to that the course may promote HRE skill acquisition in students with relevant backgrounds in cybersecurity or computer science. And this course should then enable them to participate in our study and to solve a more or less realistic hardware reverse engineering task. And second, the course should act as our study environment in which we may be able to recruit participants for our main study. And we also had to face a new problem again, because there had been no prior scientific work on how a course had to be developed that would promote HRE skill acquisition. So again, we were faced with the problem that there was no guidance or no prior courses which may have helped us to get our samples. So we had a journey over 1.5 years in order to develop and evaluate a course that we developed, and we wrote 2 papers and published 2 papers about it, teaching hardware reverse engineering and promoting the acquisition of hardware reverse engineering skills. And both papers included an evaluation with 2 experiments, 2 studies, and showed that the final course structure enabled advanced cybersecurity students to acquire a sufficient amount of hardware reverse engineering skills yeah, and thus may yeah, that they would be able to participate in our main study. I think Stefan would like to tell you a little bit more about the course, right?
Yeah, I was actually tasked with developing the course, and then we want to do a study in the course, right? So we have a theory part in the beginning, which also covers the fundamentals of hardware design, and then the influential works of hardware reverse engineering, of course, with the students. That's like for the first 6 weeks of a 14-week course. And then in the second 8 weeks, we developed like a lot of practical tasks where the students could actually apply their knowledge, practical, and work with state-of-the-art tools on realistic tasks. Yeah, those are not real-world tasks, because like a real-world netlist, can have at least millions of gates. So that's not practical for somebody who works for a couple credit points at the university. But yeah, we were actually able to come up with a lot of interesting tasks, which was then the stimulus material for our study. And as Karina already said, we continuously refined our course over several iterations till it was good, and we're actually still teaching it. So then we could actually conduct our study. But did anybody do that before? No. So we again started with a blank sheet of paper. So we had no methods how to analyze the behavior of the reverse engineers. So we basically started with some high level research goals. On the next slide, yeah, and yeah, what we already said, we wanted to explore the technical and cognitive processes during hardware reverse engineering. And then we refined it a little bit and said, okay, we want to know more about the applied problem solving strategies. We want to know something about the time efficiency, and we want to see if we can find differences between the study participants who, like in this case, were then actually a pretty homogeneous group, right? So we brought some of our research questions here. So we wanted to see, can we see actually phases of human sense making during the process? Are there certain cognitive prerequisites which play a role for the success of hardware reversing? And which of those processes can we actually see, and can we see differences in the time efficiency in those strategies? Here's some overview over our methods. So as we already mentioned, we embedded this study into the university level course. And then we said, okay, there are like 4 training tasks, and they grow, in the number of gates. They're getting more. We start with a small netlist with just like 100 gates. Those are not just and or gates, but also like some more complex gates. And we also increased the difficulty. And then in the end, we have the most complex, the most difficult task as our study task. But then we investigated the 8 top performing students who completely correctly solved the task. This is how we chose them. Yeah, so we didn't choose anybody who didn't completely solve the task. And we were lucky to get 1 expert. And our main variables were the solution time, which we measured, the correctness I just mentioned, and we collected a lot of behavioral data from the program they were working with to reverse engineer the netlist. And Karina did also like tests about the cognitive abilities. There's going to be some more information on the next slides. And then afterwards, we analyzed the behavioral log files, and we applied an iterative open coding based on grounded theory. So here's another overview about our study. So in the beginning of the course, of course, this was actually IRB approved. So it was like we made sure our study is ethical, and we follow data protection laws and stuff. And then we gave the students 2 weeks to be recruited, basically. So we had like 40 participants in the course. 22 of those participated in our study. Then we conducted the course itself, actually. if you go to the next animation, sorry. Did the 6 hours of theoretical background and did the training task with the students, which contained, for example, finding finite state machines in FSMs, or we had a substitution permutation network like an AES-like cipher, where the students had to find and identify an S box, and then if you manipulate the S box there, you can extract the key actually. In the training tasks. And then we had the study task, which actually was about some hardware watermarking scheme. So basically a watermarking you use if you want to prove that somebody stole your intellectual property. And now the participants of the study took the view of an adversary who wanted to infringe on the intellectual property and remove the watermarking. At the same point. And then we're lucky actually after we conducted the study that we gained access to one expert who had already 5 years of experience in hardware reverse engineering, who also did the task and whom we could compare to our 8 top performing participants. There's a little bit more details on the data which we collected in our study. So we collected the total solution time, which came directly from the log files and which excluded breaks. And then we collected actually a number of behavioral data, basically all their manual and script-based interactions with the Netlist and the duration of those interactions. Karina did the Wechsler Adult Intelligence Scale with the students and got those 3 subscales here, the perceptual reasoning, the working memory, and the processing speed of the participants, which we could later compare to their progress, basically. And we also collected several control variables like age, major, target degree. Yeah. And here's some details into the behavioral data analysis we did. So this is a screenshot of the Netlist reversing software. And this Netlist reversing software, it's called HEL, is actually used for real research and for real Netlist reversing tasks. So this was trained to the students before, and they could use this. And it actually also enables us to collect the log files, which look kind of like this in this table here. So they always have a timestamp. Then we know the type. So was it a script or was it a manual interaction with a component of the Netlist? And we got some additional information, like actually the script content. So they can interact via Python scripts with the Netlist. So we have all the Python scripts that they developed and all the manual actions. And then we started analyzing those. If you go one step further, we started analyzing those actions with a grounded theory approach. So we basically took a deep look into their logs, and we observed every step and we annotated every step of what they did. Like looked at the changes in each step, and then used this as a basis to explain the observed behavior. And then we continuously like refined this and extracted roughly 100 so-called open codes, which describe the behavior of, which can be used to describe the behavior of a reverse engineer. Yeah. And there are like 3 examples of those codes on the next slide. So one could be the reverse engineer applied manual Netlist exploration. And then this means that he navigated through the Netlist using the graphical user interface. Then it could also be that, that the participant developed like small test cases. Then he didn't continue developing his main script, but he actually tried some smaller functions. But we also observed like kind of pitfalls, like for example, like a dead end that that our analysts tried a certain strategy, but then gave up on that and didn't continue to follow it. Yeah. So there are going to be there's a brief overview about our results now, which were published at SOUPS 2020 last year, and then there's another paper which we submitted to the ACM transactions on computer-human interaction, and which is currently under review. Yeah. So here's again some overview about our results. So we actually could find in all our participants, in the 8 participants from the course, but also in the expert, 3 consecutive phases, which I will explain in further detail. And based on those open codes, we could come up with a detailed taxonomy for hardware reverse engineering, which can be used to describe the steps. The strategies we found were very individual. So like we didn't find like one strategy which like rules it all, but we found like different strategies which could also be time efficient. And we also got first indications that the cognitive factor working memory and of course expertise played a role for time efficient HRE performance. And yeah, within our codes, we found several unique insights into the problems doing hardware reversing, such as the dead ends, which I just talked about, and some other strategy changes. So the human sense-making phases look like this. So first, all our participants went to identify the relevant components in the netlist. So in this case, they wanted to find components which actually implement the hardware watermarking. And they used methods for this, which interpret the netlist basically as a graph. So then you can apply graph-based techniques. For example, you can search for strongly connected components. And we could also observe in this first phase of candidate identification a lot of manual interaction with the netlist. So less scripting and more manual interaction. Actually, although this took the participants only like roughly 10% of their time, like they did 50% of their manual actions. In the second step, then they further investigated and checked their candidates to narrow them down on the actual targets. This usually includes like a lot of functional analysis, a lot of going into the Boolean functionality actually, and this took the most time of participants on this task. And then, of course, if there's no candidate left after the verification, then you have to start over with phase 1 again, right? And you have to identify candidates again, which you then further investigate in step 2 again. And then the first, the third step is that you have to fulfill a task-specific objective. Here, it was to remove a watermark, but it can also be to actually clone the design or to find a hardware Trojan. Or something. There are a lot of different methods which can be used here. For example, like the simulation of parts of the netlist can take place here, and it also took a significant amount of the participants' time on task.
Okay, so I will continue with our next result. Stefan also already mentioned that the cognitive factor working memory, which was part of the Wechsler et al. Dart intelligence scale, showed an interesting result. We also have to mention that this, with the disclaimer, we only conduct descriptive analysis due to our small sample size. But what we can see here is a tendency that working memory may play a role in solving the hardware reverse engineering task quicker. As you can see, on the x-axis, we have the working memory scores and the total solution time in minutes. And yeah, the data shows that participants with higher scores in working memory tend to solve the HRE task quicker than participants with lower working memory scores. Yeah, there appears to be one outlier. But yeah, this is a tendency we found, and we want to highlight that this is the descriptive nature of this finding. because of our small sample size, but nonetheless, we think that this finding serves as a basis for future research and should be understood as the first implication. And we will outline this idea in greater detail in our future research part of this presentation, in which we aim to quantify the influence of working memory on solving hardware reverse engineering tasks. So next slide, I prepared.
One quick question.
Sure.
on the graph. Yeah. So or like actually two quick questions. So what happened to participant 3?
Participant 3 didn't want to participate in the intelligence test. So
I see.
Yeah, his solution or her solution was so interesting that we wanted to include this participant in our strategy analysis. Yeah, but we cannot force anyone to conduct our.
Of course. Yeah, right. And which one of those is the expert?
Yeah, the expert also didn't participate in the test.
Okay.
Yeah.
Okay.
Yeah. Yeah. So it's just a tendency. Yeah.
Yeah.
But,
okay.
Yeah.
Fair enough. Thanks.
Sure. Yeah. We have a little time issue, I think. Yeah, I prepared a slide with the strategies and focus some participants set in their problem solving. Maybe I just summarize this slide for you. So as our results show that besides the experts, some intermediates also achieve fast solutions. Intermediate 8 and 3 were close to the solution time by the HRE expert. What was kind of surprising is we expected that the expert might outperform the students, but he or she didn't. Yeah, and our results did not indicate that a single optimal, one and only, or end-all, be-all problem-solving strategy for most efficiently solving the HRE task existed. Rather, our analysis showed that several participants achieved efficient solution through the application of different and individualized strategies. For example, we observed that the time-efficient problem-solving strategy of the expert was based on test cases and small-step approaches, which could not be observed in this extent in the problem-solving of the intermediates. And yeah, furthermore, our results also showed that the use of external resources was the dominant strategy in the problem solving of the intermediates, which covered all actions like using external resources such as the provided coding guide, pen and paper analysis, or online resources to develop their reversing specific algorithm. In addition, we also found that some intermediates also applied a very unique approach, like intermediate 5. Participant 5's problem solving was mainly characterized by the development of a generic approach that would have been also useful to complete a similar reversing task on a different netlist. So yeah, this was quite interesting. I would love to go into greater detail, but I think we want to continue with our future research. And yeah, I go over to Stefan.
Right. So what we want to do, what we promised you, is that we want to develop cognitive obfuscation. Yeah. But what is obfuscation at all? We brought a little analogy for this. So if on the left side, this is the unobfuscated netlist, you might find out how to cut your neighbor from the phone. But if you have the same task on the right side, this is going to be quite difficult. And this you could imagine as like the obfuscated netlist, and then your task still stays like cutting your neighbor from the phone. Yeah. So this looks a lot harder, and we want to do this actually in our next steps to create tasks which overload the capacity of the reverse engineer's working memory. For example, by creating like many structures which look the same in a netlist, but which are functionally different. Yeah, so this would actually work against the phases I described before also, because then they have a lot of candidates. And then they need to go into the time-consuming step of functionally verifying those candidates. And then they all look the same, but they do different things. And for that, we're going to use low-level obfuscation primitives, which already exist. So some smart people came up with, for example, dummy wires or camouflaged gates. A dummy wire would be like a gate with, like, let's say 3 inputs. And if you take the pictures of the chip, then you see 3 inputs, but actually 2 of those inputs only are functional. This would be an example for such a low-level obfuscation primitive, which we could apply for those netlists for cognitive obfuscation. Right, so I'm briefly gonna go over this and summarize our work before Karina shows you some future ideas. So this was the first step towards the better understanding of cognitive processes in HRE. Of course, like if you look back, you could have done a lot of things like differently, but like this, I think it's always like this in research, right? We found this 3-phase model, which is going to be pretty helpful to create cognitive obfuscation. And what we didn't talk about is that we also analyzed the combination of manual and semi-automated analysis of our participants. And Karina talked about the working memory, which might influence the success of HRE. We have also to admit that there are a number of limitations in our research, which are, of course, like the small sample size of only like 8 students and only like 1 expert. And of course, we cannot generalize from the HRE problems we investigated to all HRE problems, although we think that in our tasks, we cover at least a good range of relevant HRE problems. This is also what the experts we are in exchange with, but who don't want to do our studies, tell us at least. So yeah, in the future, I just talked about if we want to implement cognitive obfuscation, but we also want to quantify the cognitive influences, and Karina is gonna use the last 3 minutes to tell you something about this.
It's also the last main slide from us now. So yeah, I would like to talk about our future work, which is also the second part of our methodological approach, which I previously mentioned. It's all about the quantification of the knowledge or the findings we gain from our interdisciplinary project. So we found that expertise, but also cognitive factors such as the working memory may play a role in achieving a time-efficient solution. But the question now is how to quantify these influences, because we won't get any larger sample sizes as we got in the past 4 years. So we developed a hardware reverse engineering game, which actually covers or simulates hardware reverse engineering subtasks in an environment which is playable or solvable without the strong amount of prior knowledge which an HRE expert might have. So our plan is to use this knowledge-free environment, the HRE game, to carry out laboratory studies, or in this during Corona, online studies, in order to observe a larger sample size how they solve those problems. And all the levels of the game are based on realistic HRE tasks. Stefan, would you like to explain some stuff about this, or
sure, yeah,
this FSM and non-linearity or something?
I think I won't go into too much detail here, but basically this represents a part of the functional analysis of finite state machines. So finite state machines are always very important in hardware circuits because they steer, the rounds of the AES or something. So usually you search for FSMs, and then if you want to manipulate the AES, then you manipulate the round counter. Yeah, and this you could imagine here as a finite state machine with a defined output, which is like the bulb and the danger symbol, so 1, 0, and then you need to find the right inputs under the logic in between to reach this output state. Yeah, this is one example task which we brought here.
Which we'll use in
and of course it's very simple. compared to real FSMs.
Yeah. Okay. This was our presentation about our PhD years. It was a combination of try, fail, and success. We hope. We've shown you some interesting insights, and we are happy to get some questions from you or some other discussion points. Thank you for your attention.
Yeah, excellent. Thanks a lot. That was really a very, very interesting talk. Let me briefly stop the stream